Welcome back. So we talked about this sugar in the previous video. We didn't give it a name, but we talked about this simplest carbohydrate that is chiral. And we said that this center carbon right here has four different groups on it. A hydrogen, an OH group, which is a hydroxy group or an alcohol group. Then we see the aldehyde functional group, C double bond OH, and then we see this CH2OH group that's hanging out down below. This is the only chiral carbon that this particular sugar has. And we said that because it's chiral, there's a R form and there's an S form. And I want to review what the R form and the S form look like, and I want to review how to draw the R forms and the S forms, because sometimes this is very important. So what we do is that we start off with a center, and I'm just going to draw kind of a dot to represent that center carbon. And there's four groups that are attached to this. So in the world of stereochemistry, what we do is that one goes straight up and down, and with the other one, if I want it to draw it, it kind of goes out to the side a little bit. So I'll just draw it out to the side. And then there's two other bonds on here. Stereochemistry is going to force me to take one of the bonds and shade it dark. And then it's going to force me to take the other one of the bonds and put a dashed wedge on it. Okay, so this kind of gives us a 3D orientation or a 3D shape concerning the carbohydrate itself, or in this case, just the chiral carbon itself. Now there's four groups attached. And the traditional rules of stereochemistry, if you're free to do it, basically tells you to put the lowest priority group in the back. You want that lowest priority group to point away from you. So we have to take a look at the four groups that we have on the center carbon and figure out what is the lowest priority. And the priority number, so priority is assigned by the atomic number. The lower the atomic number, the lower the priority, right? So out of all four of these groups, carbon's directly connected to a carbon here, it's connected to an oxygen here, it's connected to a carbon there, and it's connected to a hydrogen here. Hydrogen has the lowest atomic number, so therefore I'm going to put hydrogen on the dashed wedge. So low priority, if you can squeeze by it every time, goes on the dashed wedge of the molecule. Okay, so this gives us a place to start. The top priority, if we're giving free rein to draw the structure as we want, top priority, well, that goes up at the top of the actual structure itself. So let me just change this word top to highest. The highest priority one goes at the top of the molecule. Okay, so I need to look for now, out of the three remaining groups, the atom that has the highest atomic number. Well, this one has a carbon, that's a 6, right? This down below is a carbon, that's a 6. And the one over to the right is an oxygen, and oxygen has a 8 for an atomic number. So this is the highest atomic number right here. So the highest atomic number is going to be my OH group. So I'm going to prefer to draw that one up at the top. Now let's say that I want to draw the R form of the structure. So that means I want to draw the right-handed form, which means in the stereochemistry, I should have a rotation. And that rotation needs to point right-handed. So the molecule kind of needs to turn this way if it can. So this is my number one priority up here at the top. I now need to figure out what my number two priority is, because whatever that group is going to be, that's the group that's going to go here, because it needs to point right-handed. It needs to go clockwise. So R's go right-handed, which means clockwise around the molecule. All right, so carbon and carbon, that is a tie. So I go to the next atom now in line. I save hydrogens to the last, but I go to the next atom that's in the lineup. Well, this carbon, that hydrogen, I count it last. So the next atom here is an oxygen. And then I take a look at the group down below. Well, here's a carbon. The next atom in line is an oxygen. Oh no, we have another tie. So that means we go to the next atom now in the group. Well, the next atom down here at the bottom, we've run out of choices. The only thing that's left is a hydrogen. So I count a hydrogen there. Up here at the top, however, this is a double bond O. So that really kind of means you count that oxygen twice. We've already counted it once. Now we'll count it again. So we count the oxygen again for a second time. We compare it to the hydrogen that's left over down here. This oxygen is going to have a higher priority than the hydrogen down here. That means that the C double bond OH group has the next priority, and then that finally means the CH2OH group has the remaining priority. Now let me just rewrite this a little bit better. So CH2OH, I'm kind of going in order as they're hooked up. So that is the R form for that structure. Now what if we wanted to draw the S form? Well, the S form, if you can do the R form, you can do the S form. There's really going to be no big deal with it at all. I still start with the center. I see one straight up, straight down, one bond that's on a solid wedge, and I see one bond that's on a dashed wedge. Hydrogen still prefers to go in the back if I'm given the choice. OH still goes up at the top if I'm given the choice. And this needs to go left-handed. We're trying to draw the R here. So this is a counterclockwise rotation. So we're looking at counterclockwise. So that means left, then it goes here, then it goes there, and then it kind of goes back up. That's the rotation that we want to include. Okay, so the next group in line is the C double bond OH, right? We determined that was the number 2 priority group. In the first example, we put it here because that gave it a clockwise rotation, which was R. In this example, we're going to draw it down here because this gives me the left-hand notation, and that is the S form that we want. And then CH2OH happens here. Notice the only thing that we did. The only thing that we did is that we took this group and we took this group and we switched them. That is the only thing that happened here. And that is what toggles back and forth the R form and the S form. Two groups switch their positions and you immediately reverse the stereochemistry that's on that molecule. Alright, so there is your review, your 8-minute review of what R and what S is and how to draw structures using R and S. This shouldn't be anything new. This should be something that you should already know. If you don't already know it, then my advice is to go back to the stereochemistry portion of the text or rewatch some of those stereochemistry videos in our YouTube account and kind of brush yourself up on them because they're coming back. Now the problem here is that this is where we stopped. In chemistry, traditionally, we talk about R, we talk about S, and we don't really mention anything else anymore. However, because of biology, thank you biology, we have a different classification scheme. And instead of the R and the S, what they use is a different version. They're not really happy with the R and they're not really happy with the S for a number of reasons. So biology and biochemistry really tend to stray away from the R and the S, and they use something else that represents R. And they use something else that represents S. So, what do they use? Well, they use something called the D and L notation. And the D and the L notation basically is the same thing as R and S. There's no difference in it. The D stands for dextro, rotatory, and the L stands for levorotatory. Okay, so we get D and we get L. So D is dextro and L is levo, and it's rotatory, which means rotation, right? Rotatory and rotatory. That means rotation. So right rotation, left rotation. So the choice is up to you. In biological chemistry, you're going to see us use the D and L form when we can. However, in traditional organic, what you saw months and weeks ago, as far as stereochemistry is concerned, you saw us mention R and S only, and that was it. We called it a day. So be comfortable with both versions. So that means that this is a R rotation, but that also means that this is a D rotation as well. And this is a left-handed rotation. It was the S rotation, right? So that means that this is the L rotation as well. D and L and R and S are interchangeable. You can use D and L to describe the configuration, or you can use R and S to describe the rotation of the molecule as far as the priority goes. Now, there's something else with stereochemistry that you need to keep in mind. So all of this up here at the top, this all focuses on priority of groups. That's all that we're doing. How do the groups rotate around the carbon? Now, that was different, because what we saw is that if a molecule had a chiral center, then we also said that this thing was optically active. And optical activity basically was putting the molecule in a polarimeter and measuring, does it rotate light left-handed or does it rotate light right-handed? That had nothing to do with R, S, and D and L. They have nothing in common, period, right? D, L, R, and S are completely separate from the optical activity of how it rotates light. And there were two ways that we described optically active molecules. One had a positive and one had a negative. Positive meant that the light went right-handed, and negative meant that the light from the polarimeter went left-handed. So the take-home message here is that you can have a R plus or you could have a R minus. You could have a S plus, you could have a S minus. You can have a D plus or you could have a D minus. Or you could have a L plus or a L minus. Okay, they have nothing to do with each other at all. Well, what does have something in common? Well, we already said the R and the D can be used interchangeably. They mean the same thing. The S and the L can be used interchangeably. They are really referring to the same thing. What you should not really relate together is the plus and minuses with how the groups rotate about the carbon. They are completely different. One is the top RSDL. That is how the groups are rotating around the center carbon. The positives and the minuses are how these molecules are rotating light in a polarimeter. Now, all sugars are chiral, which means all sugars have a chiral center, which means all sugars are optically active, which means that all sugars will rotate light in a polarimeter. And this is one of the things that you'll be doing this semester. You'll be making some carbohydrate solutions, you'll be putting them in the polarimeter, and you'll be measuring their light rotation. So is it positive? Is it negative? That's up to you to figure out. But you will be doing a lab that focuses on the rotation of light and these sugar compounds that we're being seeing. By the way, these up here at the top, they were called perspective formulas, right? Don't forget it.